In this class, we are going to learn about spectral decomposition of a matrix. You know, given a square matrix, we know how to find the eigenvalues. A bunch of the eigenvalues gives us the spectrum of that matrix. Right? With the help of those eigenvalues and eigenvectors, let's see how to decompose a matrix. First of all, what is a matrix decomposition? See, sometimes a huge matrix is hard to handle. So what we do is we make it into pieces. The way of making it into factors is what we call a factorization or a decomposition. The factorization of a matrix A into two or more matrices, say M into M1, M2, Mn, such that their product M1, M2, M1, product of those matrices will give back you the original matrix, right? Now, in this unit, we are going to see different decomposition techniques. There are many things, but we basically concentrate on spectral decomposition of a matrix, QR decomposition, LU decomposition, and so on and so forth, right? Now, basically, you need to understand what does a linear transformation mean, right? A matrix A defines a transformation from one space to another space, right? If in the process, if a vector goes lambda times itself, we know that it's called an eigenvector, and lambda is called the eigenvalue, right? For example, here, look, this matrix A is transforming the black vector onto Y space like that. Green vector goes like that, right? And if the A happens to be a non-singular matrix, then dimension is preserved. Hyperspheres will go into hyperellipses, right? Example. Now, if that A happen to be a symmetric matrix, we are very lucky that we get an orthogonal decomposition, right? Meaning we can construct that V as an orthogonal matrix, and the eigenvectors will go as the axis of that ellipse or a hyperellipse or whatever, right? Right. So the eigen decomposition of A will tell us which orthogonal axis it is going to scale and by how much, right? So we can say AVI here. AVI goes as lambda VI, meaning this goes as an axis and this is the scaling factor, right? In general, if A also gives a rotation, then we know we need to go for if it's a mere scaling, then it's eigen decomposition. If a rotation also we need, then we go for a singular value decomposition. All these decompositions we'll see in each lecture, right? Now, the first lecture is on spectral decomposition, right? What do you mean by spectral decomposition? A square matrix, n square matrix, n by n symmetric matrix can be decomposed as P, D, P transpose, where P is an orthogonal matrix. That is the advantage we got if A is a symmetric matrix, right? And D is a diagonal matrix. That tells you basically how much the axis get scaled up, right? And the diagonal elements, they are the eigenvalues. We have seen in the last class in the diagonalization. Given a symmetric matrix, we can find its eigenvalues, we can find its eigenvectors. Its eigenvalues goes as diagonal elements, and its eigenvectors are used in the construction of the orthogonal matrix, right? And also we know that if A is a symmetric matrix, its eigenvectors are always orthogonal. Just normalize them. We are going to get orthonormal vectors. Thereby, with the help of these orthonormal vectors, if we construct a matrix, that becomes an orthogonal matrix, right? Then, so the expression the decomposition rather, when it decomposed, A is a symmetric matrix. When it decomposed as P, D, P transpose, then such a decomposition, we call it as a spectral decomposition of A. That is, we can write, as we have seen earlier, A being a symmetric matrix, the eigenvalues, they go as the diagonal elements, and the eigenvectors, after normalizing them, can be used in the construction of P. Thereby, A can be decomposed as P, D, P transpose, right? This is called a spectral decomposition, right? Once decomposed, sorry, once decomposed, reconstruction of A can be done as lambda 1 xi transpose. That is, lambda 1 into x1 transpose plus lambda 2 into x2 transpose plus lambda n into xn transpose, right? Let lambda 1, lambda 2, and so on lambda n be the eigenvalues of A, and x1, x2, xn be the corresponding orthonormal, after normalizing them, orthonormal eigenvectors. Then the spectral decomposition of A is given by A equal to lambda 1 x1 transpose plus lambda 2 x2 transpose, so on lambda n xn transpose, right? That's basically reconstructing back A. And if we put these lambdas in an order, then the eigenvalue of largest magnitude, we call it as a dominating eigenvalue of A, right? So the spectral theorem or a spectral decomposition says like this: if A is a symmetric matrix, A can always be written as P, D, P transpose, where P is constructed with the orthonormal eigenvectors of A, and later we call them as a principal axis, right? All the data will be around this axis, right? If A represents a data matrix, right? And D and P transpose, right? Example. Let's see a couple of examples. Suppose A is, this is a symmetric matrix, get its eigenvalues, mean, form the characteristic polynomial, right? That A minus lambda equal to 0 is the characteristic equation. We have seen that last class many a times. And this is the characteristic equation, get its roots. Its roots are minus 1, minus 1, 5, and 2. Look, all of them are distinct. So the eigenvectors will be orthogonal, right? So you find the corresponding eigenvectors. That is, eigenvectors corresponding to lambda equal to minus 1, eigenvector, an eigenvector corresponding to lambda equal to 5, and an eigenvector corresponding to lambda equal to 2. Right, we know the process. We have dedicated a couple of classes for that. Now, since we have 3 distinct eigenvectors, we know that since they are distinct, we know that it's diagonalizable, right? And let us construct the orthogonal matrix, right? Orthogonal matrix has to be constructed with orthogonal vectors which are normalized. So what we do is, let's normalize them, right? Look, they are all orthogonal. 2 into minus 2, minus 4, plus 2, and plus 2. x1, x2 are orthogonal, x2, x3 is orthogonal, x1, x3 are orthogonal. And let's find its magnitude. Its magnitude is root of 4 plus 9, 3. Root of 9, it's 3. Here also it's 3, right? So here we have normalized it, right? Now P is an orthogonal matrix. So P transpose will become P inverse, right? And finally, that's all. We got a P, we got a D, and once we know P, getting a P transpose is a pretty simple job. That's how A can be written as a P, D, P transpose, right? So this, the crux of the entire discussion is The spectral theorem says that if A is a n by n symmetric matrix, then if A has n real eigenvalues, we know its eigenvalues are real, right? For each, I mean, if they're all distinct, then the eigenspaces are mutually orthogonal, mean the eigenvectors are mutually orthogonal, right? And A is orthogonally diagonalizable. Let's take an example where the eigenvalues are repeated. For example, you consider this A. This is the characteristic polynomial equal to 0, lambda equal to 2, 2 and 4, right? So lambda equal to 2 is repeated twice and lambda equal to 4 is 1. And this is the eigenvector corresponding to lambda equal to 4. Let's get an eigenvector. We need to pull out two eigenvectors from the eigenspace corresponding to lambda equal to 2, right? And this is the solution vector of the homogeneous system. Then take t equal to 1, s equal to 0, then minus 1, 0, 1, and is an eigenvector. And we are free to choose any values because they are arbitrary, right? And take t equal to 0 and s equal to 1, t equal to 0 and s equal to 1, that leads to minus 1, 1, 0, right? Now look, are they orthogonal? Let's see. 1 plus 0 plus 0, they are not orthogonal, right? So first we need to choose them as orthogonal vectors, then we need to normalize it. There are two ways, right? But best way is, we have discussed earlier, Gram-Schmidt orthogonalization process. So let us choose x1, x2, x3 as an orthogonal vectors, right? Now let v1 equal to minus 1, 1, 0, this one. Then we need to project this, this onto this one, right? That's what our Gram-Schmidt process says. Now v2, we need to construct v2 is a b2 minus, right, the projection of v1 onto this space, right? So this is what happens. v1 dot b2 equal to this equal to 1. What is it we are doing? Basically, we are using orthogonalization, Gram-Schmidt orthogonalization process, and we are choosing, from linearly independent vectors, we are constructing an orthonormal basis, right? Finally, the process is discussed. I have dedicated one class for that, go back and listen again. So for end of the day, this is my V2. Now look, my V2 will be orthogonal to V1. You can cross check. V2 is minus 1, 2, and minus 1, 1, 2, right? So minus 1, 1, 0 multiplied with this is a 1, a minus 1, and 0. It's 0. They are orthogonal. Now let's normalize it. Right? This is where I normalize it. Now let's construct our P. Right? This is my P. This is my P. And what is the diagonal elements? Right? What are the eigenvalues? So 2, 2, and 4. They are the eigenvalues. So they go as diagonal elements. So P is this, D is that, and P transpose. So the spectral decomposition of this matrix is P, D, P transpose, right? That's what I mean by a spectral decomposition. So a symmetric matrix can be decomposed as a product of an orthogonal matrix into diagonal matrix and transpose. It's transpose.